In this video, let us learn about directed paths, walks and circuits in digraphs, and also learn about the connectedness in digraphs. Suppose if I have a graph, in fact a directed graph like this. The vertices, I'll name them V1, V2, V3, V4 and V5. Edges E1, E2, E3, E4 and E5. When I consider these two vertices, suppose from V1 to V4, if I have to walk, then I'll take up this direction and this way I'll reach this, or else I can take up like this also. So I can say there are two paths, means it's a sequence of vertices and edges. Along with this sequence I can reach from V1 to V4. The thing is, this is directed directed path I'm taking. Since from V1 I'm taking this direction, along E1 I'm reaching V2, with E2, V3, E3, E4. So I'm reaching from V1 to V4. It's a sequence of vertices and directed edges. Along with the sequence is called a directed path. But whereas if I take a sequence of vertices and edges without any orientation like this, then it becomes a semi-path. So there is a distinction. With the orientation, if I am going, then it is a directed path. Without any orientation, if I am going, then it is a semi-path. So the word path in digraph could mean either a directed path or semi-path. A sequence of vertices and directed edges along with the sequence is called directed path. It's called directed path, whereas a sequence of vertices and edges without proper orientation is called semi-path. Here in this graph, if I consider V1, E1, V2, E2, V3, E3, V4. This is a directed path and this is a semi-path. V1, E5, V5, E4, V3, E3, V4. This is a semi-path. So always remember, path in digraph refers to either a directed path or semi-path. Next is directed walk. A directed walk from a vertex Vi to a vertex Vj is an alternating sequence of vertices and edges. But the thing is, beginning with the vertex Vi and ending with vertex Vj, such that each edge is oriented from the vertex preceding it to the vertex following it. Okay, always remember that a directed walk, when I consider from particular vertex to any other vertex, then that will be a alternating sequence of vertices and edges, but each edge is beginning with the vertex Vi and ending with the vertex Vj, and there is a orientation. that will be a directed one. When I consider semi-walk in a digraph, it is a walk in the corresponding undirected graph, but it should not be a directed walk. Okay, semi-walk should not be a directed walk, but it is a walk when I consider this undirected graph of this directed graph, then that is a semi-walk. And always remember, no edge in a directed walk appears more than once, but vertex may appear more than once, just as in case of undirected graph. Next is circuits. Circuits in digraphs. There are two types of circuits again, semi-circuit and directed circuit. For example, if I consider this, I'm starting from V1, E1, V2, E3, V3, and I'm coming back to V1 through E3. So that this will be a directed circuit. But if I consider like this, say V1, V2, V3 with the edges say E1, E2, E3 like this. Okay. In this case, if I start from this way, then V1, E2, V2, E3, V3, E1, and I'm coming back to V1. This both are the circuits only, but this has got proper orientation. Therefore, this is directed circuit. And in this case, I'm starting from V1, take this way, and this way. But here, this is opposite direction. Therefore, even though this is circuit with the directed edges, but orientation is not proper, so we call it as semi-circuit. Next is connectedness in digraphs. If it's undirected graph, we say graph is connected if there exists a path between every pair of vertices. There exists at least one path between every pair of vertices. But in case of digraph, there are two types of paths. We have two different types of connectedness in digraphs. A digraph G is said to be strongly connected if there is at least one directed path from every vertex to every other vertex. If there exists at least one directed path from every vertex to every other vertex. Then we say graph G is strongly connected. And a digraph, I mean always I am taking digraphs only. A digraph G is said to be strongly connected if there exists at least one directed path from every vertex to every other vertex. A graph which is not strongly connected is called weakly connected if its corresponding undirected graph is connected. If its corresponding undirected graph graph is connected. But note one thing, it should not be strongly connected. See, when I take strongly connected graph, if G is a digraph, okay, that is strongly connected. Even if I take its undirected graph of G, that will be connected, okay. To say that graph is weakly connected, that should not be strongly connected, and its corresponding undirected graph must be connected. Then only I can say that it is weakly connected. Let me draw examples. And these two graphs, when I consider this graph, between every pair of vertices, there exists one directed path. See, from here to here, if I can, I have this path. From here to here, I have this. From here to here, I have this. So, in this graph, say G1, between every pair of vertices, there is a directed path. Therefore, I can say this is strongly connected. But in this graph, see, this is not strongly connected, because if I take these two or any two vertices, if I consider these two, if I consider, there is no directed path, right? Therefore, I can say this is not strongly connected. I have to check whether it is weakly connected. It's not strongly connected. To check weakly connected, I just have to take up its undirected graph. This is its undirected version. So this is connected now. Therefore, I can say that this graph is weakly connected. So when the graph is given, first you have to check for whether it is strongly connected or not. If it is not strongly connected, then take its undirected graph and check whether it is connected or not. So when I consider undirected graph, I can say this is connected if there is at least one path between every pair of vertices, so that this undirected graph is connected. So if it's not strongly connected and its undirected graph is connected, then I can say that it is weakly connected. Suppose, say, I have some graphs like this, which has got some components. Now this. Now see, this is not strongly connected, and I have to take its undirected version. So that comes out to be like this. But this undirected version is also not connected. Therefore, I can say this is disconnected. Disconnected graph or digraph. Disconnected graph. This is its undirected version is also disconnected. Therefore, I can say that this is disconnected graph. So a digraph that is not connected is dubbed as a disconnected. Okay. Since there are two types of connectedness in a digraph, we can define two types of components also. Okay. Each maximal weakly or strongly connected subgraph of a digraph is called component of G. Say when I have digraph, its subgraphs I am considering, and maximal subgraph, which may be weakly connected or strongly connected, that maximal subgraph is called component in case of disconnected digraph. Okay, and within each component I can find each maximal strongly connected subgraph, that is called fragment. I repeat, if I have disconnected digraph, then each maximal weakly connected or strongly connected subgraph of that digraph is called component. And within each component, if I can find maximal strongly connected digraph, then that is called fragment. I'll explain it with an example. This is my example. Suppose I have this graph. It's a directed disconnected graph. Now this has got two components. One is this, another one is this. Say let me take this as component 1. This is component 2. G1 and G2 are the components. See, it's a maximal subgraph, maximal weakly or strongly connected subgraph of a digraph. This whole is a digraph. Each maximal weakly or strongly connected subgraph of a digraph is called component. So G1 and G2 are the components. It may be, this subgraphs may be strongly connected or weakly connected. Now within each component, if I can find a maximal strongly connected subgraph, then that will be a fragment. So in this case, for G1, maximal strongly connected subgraphs I have to check. So when I consider this E2, E1, this is directed, okay, and I can say this part is strongly connected. So fragments of G1 or fragments in G1, that is, one is E1 and E2. Okay, and another thing is if I consider this self loop, this is also strongly connected, therefore strongly connected subgraph. Then E5, E6, E7, E8. This is also strongly connected. There is a path between, directed path between every pair of vertices. So E5, E6, E7, E8. So this is strongly connected subgraph of this component. Therefore this is one fragment, this is another fragment, and this self loop is one more. And then let us look at the fragments of component G2. 11, 12, 13. This forms a strongly connected, this is a strongly connected part, subgraph of this component G2. Therefore, there is only one fragment in G2, that is E11, E12, E13. Okay. So you can observe one thing that E3, E4, 3, 4 and E9 are the edges which are not appearing in any fragments of G1. So this is about fragments, and depending on this, we learn one more thing, that is condensation. They say denoted as GC, the condensation GC of a digraph G in each strongly connected fragments is replaced by a vertex, and all directed edges from one fragment to another are replaced by single directed edge. I repeat, a condensation GC of a digraph G is a digraph in which each strongly connected fragments are replaced by a vertex. See, this is a strongly connected fragment. This one this one and this one. What I'm doing is I'm replacing the strongly connected fragments by a vertex. These two edges I'm replacing it by a vertex, and this whole fragment is replaced by a vertex, and one more is this. I'm replacing it by a vertex, so that this will become the connected is this 2 is connected with this, and this whole thing is connected and replaced by a vertex. So now this vertex is combination of edges E1, E2, and there is a direction like this. Then this vertex is a combination or condensation of edges E5, E6, E7, E8, and this is edge E9, and with the condensation of the vertex of the fragment E10. This is the combination of E3, E4, I say. E3, E4. So each strongly connected fragment is replaced by a vertex, and all directed edges from one fragment to another fragment replaced by a single directed edge. See, from this fragment to this fragment, these two are the directed edges, that is replaced by single directed edge. So for this whole fragment is replaced by a vertex. This will be there, E14. So this whole part is E11, E12, E13. So this strongly connected part is replaced by a vertex, and the directed edges from one fragment to another fragment is replaced by single directed edge. So this is nothing but the condensation of a graph G. Note that the condensation of strongly connected digraph is simply a vertex. Okay, it's simply a vertex. And condensation of a digraph has no directed circuits. See, when I draw condensation of a directed graph, I'm not getting any circuits. Okay. One more type of digraph. We have studied Euler graph. Now we'll look at Euler digraph. Euler digraph. In case of one directed graph, if a graph has an Euler line, then I can say it's Euler graph. But in case of digraph, in a digraph, if G is a closed directed walk which traverses every edges of G exactly once, then I'm saying it as it has got an Euler line. And a digraph containing Euler line is called Euler digraph. In a digraph G, a closed directed walk which traverses every edge of G exactly once is called a Euler line, and a digraph containing Euler line is called Euler digraph. This is an example for Euler digraph. See, this digraph contains Euler line. So when the graph is given, I have to check for the Euler line. Euler line is a closed directed walk which traverses every edge exactly once. Okay. So if I start from here, this vertex, I'm taking A, B, C, D, E, F. I can come back, so that this is a closed walk, therefore which is traversing through every edges. Therefore I can say this has got Euler line, and I can say this graph as Euler digraph. Now the thing, So the thing is, when is digraph is an Euler graph? Clearly, the digraph must be connected with the possible exception of isolated vertices. Otherwise, every edge cannot be traversed in one walk. In fact, an Euler digraph must be strongly connected, although every strongly connected digraph need not be an Euler digraph. So let us provide a very simple test for determining whether a digraph is Euler digraph or not, or whether the digraph has Euler line or not. That is by proving this theorem. A digraph G is an Euler digraph if and only if G is connected and balanced. What do you mean by balanced digraph? Balanced digraph is a digraph in which for every vertex V in G, invalency is equal to outvalency. D minus of Vi is equal to D plus of Vi for every Vi in G. This I have mentioned in my last video. So now let us prove this. It's quite easy. I'll take up first part. I'll assume that G is an Euler digraph. When I say it's an Euler digraph, then G contains an Euler line. If I say G is Euler digraph, then it contains Euler line, contains an Euler line. Hence, I can say that every edge in G is traversed in one walk, and I can say G is connected. See, when I say it has got an Euler line, then in one walk, I can traverse all the edges of G in one walk. By one walk we can traverse every edge of G. Therefore I can say that G is connected, right? So one thing is over, connectedness is over. Then I have to check for the whether it is balanced or not. So for that, for each vertex, there is a directed edge preceding it and one following it, since it has got an Euler line. Okay, G has an Euler line. Therefore, I can say that for each vertex, there is a directed edge preceding it and following it. It means that in degree of a vertex is equal to out degree of a vertex. Therefore, in degree of a vertex is equal to out degree of a vertex. That means that's same as writing D minus of Vi is equal to D plus of Vi. This is for all Vi in G, right? That means the graph is balanced. This is the first part. If I take the second part, if the graph is connected and balanced, then I have to prove that it is Euler digraph. Say assume that the digraph is connected and balanced. I'll assume G is connected and balanced. Then there is a directed path from every vertex to every other vertex. Since I have mentioned it is connected, so there is a directed path from every vertex to every other vertex, right? Therefore, and that's also mentioned that it is balanced, and so I can say d plus of vi is equal to d minus of vi for all vi in my graph G. Hence, I can say for every edge entering a vertex, there exists an edge to exit, right? Since it is mentioned in degree is equal to out degree, means balance. So for every edge entering to a vertex, there exists an edge to exit. That means there exists a directed walk which passes through all the edges. Since graph is balanced, for every vertex in degree is equal to out degree, right? So for any edge if I consider, there exists an edge to exit. That is true for all the vertices. Therefore, there exists a directed walk. Which passes through all the edges. Passes through all the edges. Therefore, G will contain an Euler line. When I say there is directed walk which passes through all the edges, that means it's a Euler line. So G has got an Euler line. Therefore, G is Euler digraph. See, remember, it's not, you may get confused. I'm getting a directed walk. It's not a closed walk like that. You may get confused, but it's not the thing, since for every vertex in degree is equal to out degree. So I can come back to the same vertex. Therefore, there exists a directed walk which passes through all the edges, and I'm coming back to the same vertex. Therefore, this has got an Euler line. Then when the graph has an Euler line, I can say that graph is a Euler digraph.